Sanibonani dumelang. Hi everyone, molweni nonke. My name is Noluto Magwati and I'm currently doing my honors in zoology at the University of Fort Hare in Alice Campus. For today's code talk, I will talk you guys through the introduction to modeling. We have this hierarchy of models that we use in HPW to explain to you guys why planet Earth is so habitable out of all the planets that we have. And for today's code talk fits everywhere in this hierarchy of models. For this code talk, I'll be focusing on models as an easy representation of a system, whereby they can be used to explain how past events occurred, such as the extinction of dinosaurs, and also predicting future scenarios such as the climate change, how will it be in the 15 years to come, and understanding the modeling process which requires to identify the real-world problem. And after identifying it, you have to know and develop a model for that problem. And also, how is this topic applied in earth science system? Meaning, why South Africa is so special when it comes to this core talk. What first comes to your mind when someone is talking about a model? I bet this is what comes to your mind. A picture of beautiful fashion models is shown in figure 1. But I'm not here to talk about that. I'm here to talk about the scientific model, which is an easy representation of a system. It can represent objects, phenomena, and physical processes in a consistent and logical way. Meaning, models are a mental visual way of linking a theory with an experiment. Therefore, what is the difference between a fashion model and a scientific model? There's no much difference, it's just that scientific model is a way of linking theory with an experiment, whereby fashion model is all about making clothes for people, mimicking someone else. An example of a model includes a computer-generated model of a dinosaur as shown in figure 2. How scientists came about with this type of a model? They gathered information that they learned from fossils and other observations in order to build this type of an organism. And also, if you take a look at figure 3 and figure 4, we have a model aeroplane in figure 4 and we have a model car in figure 3. For instance, if Mercedes company wants to produce a new car, they can't go and make the real car. They have to make a model of that car. In order to throw projections like changing the windows, the wheels, meaning that they have to make something that will mimic the real thing that they want. We have so many types of models. That includes physical, mathematical, conceptual, and empirical model, and many more. But for this core talk, we'll be focusing on the first 3 types because they're the most used ones. Once scientists have tested and explained their phenomena, those explanations are called scientific models. When it comes to physical models, it's all about physical objects that mimic the real system, meaning physical models are tangible things, something that you are able to see with your naked eyes and you can able to touch it. For instance, if you take a look at figure 5a, we have a human anatomy model, whereas in figure 5b we have a human and a human anatomy model. So we all know that it is illegal to kill a person. So for scientists to understand how the internal structure of a human being is structured, they have to make a model of a human. But however, this human anatomy model is so wrong because a human being can speak, whereas the model cannot speak. And I can walk, so as you, but the human anatomy model cannot walk. But however, it is so useful in understanding how the internal structures are structured and how they function. Going to the mathematical model, it is made up of numbers and equations and other forms of data. We have 2 types. We have the numerical model and we have the statistical model. When it comes to the numerical model, we already know the equations, but we don't know the data. For example, the Newton's third law of motion, that states that if we have 2 objects, object A and object B, when object A exerts a force on object B exerts an equal force to object A, but in an opposite direction, meaning FA is equal to minus FB. We already know the formula, but we don't know the value of FA nor the value of FB. But when it comes to a statistical model, we already know the formula, but we don't know the data. For instance, if we have 20 buffaloes that are migrating from Alice to KwaZulu-Natal, maybe we know that there are 15 male buffaloes and 5 female buffaloes. But however, we don't know the formula to use in order to understand the migration of these animals. That is the difference between the numerical and the statistical. With the statistical, you don't know the formulas, but we know the data. But when it comes to numerical, we know the equations, but we don't know the data. But it's in our human nature to forget. Yes. So we use computers to generate the mathematical models because they make fewer mistakes, and then they can keep track of more variables than any human being can. For instance, if you take a look at figure 7, we have an example of a computer which is used to generate a mathematical model as shown in figure 7. When it comes to conceptual models, it's all about scientists taking all the concepts in order for us to understand how a certain thing occurs. For instance, the idea that life originated from chemicals. Scientists gathered concepts to make us understand how life originated from chemicals. For instance, if you take a look at figure 8, we have a biosphere. In order to understand the behavior of animals in this biosphere, scientists gathered information using concepts, meaning that they built their model using the concepts to explain to us how these animals behave on this biosphere. So when it comes to conceptual models, it's all about taking models, making a model out of concepts. The modeling process is the process of representing the real world system, making it simpler from a complex problem that occur in the real life. For instance, we have the complex problem, but scientists try to break it down in order to be more simpler, in order to solve it. We have this kind of complicated modeling process, but worry not, I'm here to help you. The first step for this modeling process, we have to identify the real world problem. You can't solve a problem without knowing the problem. Yeah. For instance, let us say you want to cook a chicken. First of all, before cooking the chicken, you identify that your family is hungry. That means that is the real world problem. Then you go to your step 2, which is model development. Your step 2 when it comes to the chicken is you have to cook the chicken. But in order to cook the chicken, you have to take all the ingredients that you will need. For instance, the potatoes, the chicken, the spices, and other things that you will need. That is your step 2, model development, which requires approximation and parameterization. But we have to explain the word parameterization. Let us say you are busy on online dating with this person, but we don't know that person that very much. You ask the guy to send you his picture. And the guy decides to send you the first picture, which shows the outline only. But however, you're not happy with this picture, you ask the person because you cannot see the person very well. It's still dark. It shows the outline only. Then you be like, can you please send me another picture? Because this one is not very clear. The person, in order to send you the second picture, needs more data. And then he gets the data and sends you the picture again. But you are not happy with this picture because it is of a low resolution. And then you'll be like, can you please send me the picture again? And then for the person to send you the picture again will need more data. And the person sends you the picture again. And ta-da, this is the picture. This picture shows very well, it's of a high resolution. It shows everything in this guy. Just like the Paris that is settled in red. Yeah. Now you're confident and you have validated that this is the guy that I want to be with. That means parameterization is the process of deciding and defining the parameters which are needed to complete a model. Then going back to our basic modeling process and using our chicken example, we are still in step 2. Okay, you need to know what ingredients you need to complete cooking the chicken. So you say, okay, I'm gonna need potatoes, I'm gonna need spices, I'm gonna need chicken, and the pot and the stove. Then that means you identify your parameters that you will need to complete the chicken. And then you have to validate and verify, is this potatoes gonna be enough for this chicken? Is this spices gonna be enough to make it taste more nicer? That means you're now validating your parameters that you have already collected. And then you go to your step 3. Step 3, which is your results. You're now done cooking the chicken. And then that is your step 3. And then you go to step 4, which are your results. You now need to test your results. You test for validation. For instance, with the example of a chicken, is this chicken taste good? That means you test for validation. But if it does not taste good, you throw projections and analyze the chicken. What needs to be changed from what you've cooked? And then you go to your conclusion, which is step 5. You have to conclude that this chicken was, you cook it right in a right way, or this chicken needs to be processed furthermore. And then you go to your step 6, which is you need to know that have you solved the real world problem. And if it was solved, you go back to your step 1, which is the real world problem. After cooking the chicken, now you can dish it out for the family. That means you have solved the problem, sorry. And then if the problem was not solved, you have to go back to step 2, which is model development. Whereby you begin adding more spices, make it more nicer, and many more, and doing many more things. That is your basic modeling process. Now we go to a more problem analysis in a scientific world. In this case, we have our step 1, which is you have to identify your real world problem, which is why Earth is so habitable. A hypothesis was projected that says Earth is habitable because it is right distance from the sun. But to test this hypothesis, a model needs to be generated and applied in order to validate it. And our step 2 is model development. The data was gathered, the energy, the radiation, and parameterization, which is the process of deciding and defining the parameters that you will need to complete your model. And your step 4, which is a developed model. A Stefan-Bosch law was projected. And if you take a look at these equations, you guys already know this. It was plotted in not too hot, not too cold. It's just right. For instance, they took the average of albedo for the Earth. Instead of going in each and every part of the Earth, measuring the albedo, that was going to take them years. So they took the average of the albedo. And the parameter values for the model that they developed, it was computerized. Because when it comes to numbers, we need computers, as I've said before. And then they came up with a temperature of minus 18 degrees. Minus 18 degrees, that is so impossible for life to live in this earth. So a conclusion was drawn that distance from the sun is not the only factor that is accountable for the right temperature for the earth to be habitable, meaning that the real world problem was not solved. They had to go back to their step 2, which is model development. And in their step 2, they added the light and the air. Disclaimer by George Box. He said all models are wrong, but some are useful. For instance, taking an example, the human anatomy model and the real human. I can walk, I can speak, but the human anatomy model cannot speak nor talk. That is why it is so wrong. But however, it is so useful when understanding how the internal structure of a human being is structured without killing a person, because we already know that it is so illegal. So why is this introduction to modeling important? It helped us to understand how past events occurred, just like the extinction of dinosaurs. We were never there, we were not born, but we are able to know how they went extinct. And then understanding our present. For instance, we can predict tomorrow's weather using modeling. And also predict future scenarios such as the climate change. How will this climate change be in the next 10 years to come? Then where is modeling applied? It is applied everywhere. For instance, it can be applied in economics whereby they are forecasting future economies or sales. And also in social sciences whereby they are now trying to understand the distribution of populations, age and sex. And also in environmental management, which is predicting climate change maybe for the 20 years to come, 10 years to come using modeling. Has model changed over time? Oh yes, they do change over time. Models started as equations, but now they are computerized. Therefore, a scientific model must always be subject to changing. Because scientists always understand things better than before, now they have to change the models. And once a model is not right, or it did not solve the real world problem, a modeling testing has to be done because the model was wrong, or the data which was used to modify the model was incorrect. And an example of a model that has changed over time is an atom. The first scientist who came up with a model was Dalton. He said all matter consists of tiny little things, and he named them atoms. But little did you know about electrons, the nucleus. Then later on in 1986, Thomson said, you know what, Dalton, you were right, but there's something missing. An atom consists of negatively charged electrons that float in a positively charged soup. Thus, his model of an atom was called the plum pudding. Later on, Rutherford said, you guys were both right, but there's something missing. In an atom, there's a nucleus. This nucleus consists of positively charged electrons, and then which is surrounded by negatively charged electrons. Then later on, Niels Bohr said to the proposed atoms models, he said, oh, you guys are right, but there's something missing. Atoms do have electronic orbitals. And then his model was accepted. But today we're using the Niels Bohr law and the quantum mechanical model. But a problem with this quantum mechanical model is that it uses numbers. So it has people find it difficult to use it. But we are using the Niels Bohr law and the quantum mechanical model. So problems with models is just that models have limitations. It is never is the real thing. And also model results are not exact, rather than approximations. For instance, scientists would say that climate change will be worse by 5 times when comparing to this current situation. But when we arrive in 2020, for instance, it will be less than that 5 times, meaning that it was not exact what they predicted. And also the quality source for validation of model may be unavailable sometimes, meaning you can't complete your model because there's no data. Why South Africa is so special when it comes to modeling? South Africa is currently developing its own climate model that is a wow. And also in 1973, Pittman from the University of Witwatersrand, he had developed a rainfall runoff model that has been modified and used extensively in South Africa. So in conclusion, I have said that models is a representation of a system in a simpler way. And also they are used to understand how past events occurred, such as the extinction of dinosaurs, and understanding our present being. for instance, predicting tomorrow's weather, and for predicting the future using models such as the climate change thing. We are now able to understand how the climate change will be in the next 5 years to come. And modeling process is the process of developing a model to solve the real world problem, meaning that you need to know the problem before solving it. And then we have mentioned that why South Africa is so special when it comes to this topic, because it has developed its own climate model. Thank you so much. I hope you all understood this talk.